the end of the last video, what I was telling you was this idea that there's a very general statement for testing a model, and that is you take the likelihood of the model based on the data that we have observed, and you weight that by how much we believe that model is reasonable. And so you mathematically come up with that representation of how plausible you think it is. And this product of the likelihood and our prior belief is our new belief in a model. This is the Bayesian framework for model testing. And so that comes from Bayes' theorem. This guy Thomas Bayes, although this is actually probably not a picture of him, but it's the closest thing that we have. He was a cleric in Britain in the 18th century, and he was interested in gambling for, I'm sure, purely spiritual reasons. And he came up with this way of talking about our belief in the fairness of, say, a roulette wheel, given the spins of the roulette wheel that we've seen, is equal to our previous belief in the fairness of the roulette wheel times how likely the spins that we are going to see right now are given the model that we're looking at, divided by how surprised or plausible we think this data that we're observing are. So theta is the model, specifically the parameters of the model. X is the data, or data set, right? And so the probability of the model given the data is this one. This is the prior belief in the model, or the prior probability. This is the likelihood of the model given the data. And this is our prior belief in the data. It's the prior probability of the data. And so this theorem here lets us compute the probability of the model given the data. So this is not the likelihood. This is better than the likelihood, because this is a true probability. You can compute these probabilities for every possible kind of data and every possible parameterization, and those will all add up to 1 and be a nice probability distribution. So this is more powerful than the likelihood. And it's got some things here. So this when we can end up updating it with data. Like this could be the output from our previous analysis using Bayes' theorem. But when we start, it's some probability distribution of how the parameters theta are, with a larger value when theta seems plausible and smaller when theta doesn't seem plausible. And it can be a subjective belief when you start, but it's one that has been given specific quantitative form, and so that it's something that other people can immediately and identically copy. And then this is the likelihood that we calculate as normal. And so those two things, so that's the how plausible we think the model is times the fit of the model, and that's where this general framework works. This last part, the denominator here, prior belief in the data, this is the thing that you divide all these products by, so that the whole thing ends up having an area of under the curve of 1, making it a probability distribution. But it turns out this doesn't change across the data. So if we're comparing a bunch of different parameterizations or even models with different parameters using the same data, then this number is the same everywhere and we can ignore it. Whenever this is biggest, that is going to give us our model with our highest posterior probability. So this equation has a ridiculous number of applications, and any statistical test can be framed in terms of this model. However, many of those framings are extremely mathematically intense and complicated. So, for example, just for a normal distribution, you have to say what you think the probability of any combination of mean and standard deviation might be to specify your prior to compute it. And that is a pain. So, nowadays, computers are fast enough to do this, but for the first 400 years or so or not 400, 300 years of Mr. Bayes' theorem, it was a nice idea, but no one would actually use it. Now, it is the fundamental part of how people compute things in stats. so if you go on to do stats, you'll use Bayesian statistics most of the time. However, what we're going to be learning about in the rest of this course are things called frequentist stats, which don't use this equation, but do make the math really easy. Unfortunately, that means that there's some logical convolutions that we have to do when we're framing the question, which was what we're going to talk about next week. And so basically, Bayes' theorem, the concepts when we're explaining the narrative are easy, but the math is grossly hard. And in frequentist statistics, which we're going to learn about, the math becomes pretty straightforward, but you have to do a little headstand to make the narrative work. And that's one of the reasons why people don't like stats, and that's one of the reasons why we went through all of this background. So hopefully you understand it a little better. Thanks for listening.